Okay, I think that's working. Okay, so today I'm just going to go through how to, I guess, quantify different distributions. Uh, the main thought process is we'll start from the beginning and see if we could actually get to something similar to KL divergence. So, yeah, let's get started. Let's say we had two sets of dice. So we had one set of dice, like 1, 2, 3, 4, 5, 6. We had another set of dice, same exact thing. Let's check on. So one set of dice, 1, 2, 3, 4, 5, 6. Another set of dice, 1, 2, 3, 4, 5, 6. And the question is, how would we deal with, how do we quantify if we had? Why start with dice? Let's start with coins. Makes it easier. So we have two coins. It could be 0 heads, 1 tails. And so two sets of coins. And we want, and the probability for this one, let's say is 0.5 heads, 0.5 tails. And the distribution for this one would be, let's say, 0.6 and 0.4. So I guess the main question is how do we determine that these two things are different, or like how different are they? So let's think. So first I would just assume, we would take the difference of these two. So we could just say the probability of, heads minus the probability of heads here, minus the probability of tails here, minus the probability of tails here. And so let's start with that. So let's assume we had 0.5 minus 0.6. And then we would do the same thing. So this would be heads, this would be tails, and here would be 0.5 minus 0.4. I really like this tool, but sometimes selecting the numbers is quite annoying. But it is really cool and it looks really nice. Feels like a whiteboard, but with a mouse and keyboard. Okay, so heads, that would be 0.1 or negative 0.1. This would be 0.1. Now, the reason I'm doing this, I guess, is just to learn everything from the ground up, but even to take it a step further and just see how I would quantify these things, just if I didn't know the KL divergence formula. So we have heads, we have tails, we got the difference between, the two, the probability of heads in this case versus this case is negative 0.1, this case versus this case is 0.1. So now we have to think how would we quantify these things properly, or combine these numbers and to make it one official, this is the difference between this case and this case, or this coin and this coin. I could try summing these, but I feel like if I sum these, this will just be equal to 0, and summing never really works so nicely. I'd probably take the square root of these things, so try to do like a square difference. Yeah, so I'd probably first here. First, square these. Just, or we could take the absolute value, but let's square this and square this, just to deal with negative values, and everything will be a little more uniformed. I know I probably should know this, but yeah. 0.01. This was 0.01. Okay. So now that we know, yeah, it's weird. It's weird recording even because I mean I don't even think anyone's here. Oh, 2 views, nice. I guess. um, yeah, just weird. Just thinking out loud while I'm recording. I'm not used to this, but I'll get more and more used to it as time goes on. Again, just to recap what I'm trying to do. I'm trying to basically create KL divergence by hand, but like seeing how I would actually get to a difference in probability metrics. Like the goal is to go from, we have two coins, we have coin A and coin B. Coin A has probability of heads equal, and then coin B has zero 0.6 and zero 0.4. And it's just trying to determine, you know, how do we quantify this difference in probabilities of each coin. So right now I just started with, you know, heads being the square difference, tails being like the probabilities being the square difference, and we would get to, you know, 0.01 for each is the difference metric. So then we could maybe sum these up now that they're a little more normalized, and this would give us a score of 0.02, and we would say, like, I guess the divergence between, you know, the difference between this coin and this coin would be 0.02. I feel like the issue with this would probably be, it's like, I think the issue with this would most likely be it's not going to, I mean, maybe it would work out well. Let's see. So, what would be a good example, I guess, to see if something like this works out well? I guess we could look at the machine learning example where we have a prediction. We have a prediction, and then we have the actual results. And would this actually, could this be used as a loss metric to train our model properly? So let's say this is true. I wonder if I could go to concurrent. If how I could go to chat. One of these days, we'll figure this out later. So let's say we had a probability or prediction, and that was, let's say these are soft max values, so it's probability distribution 0.2 and 0.8. It's simple. And the true values were 1 and 0. Now let's say I went through my, you know, method of my current simple method of squaring the differences and then adding them up. Would that make a good, you know, just method of this? I mean, I guess one issue I could see is like if we had more value, like this isn't going to normalize well. Like if I had 10 different values instead of 2, it's going to be a lot, it's just going to get bigger and bigger. Like let's say instead of heads or tails, it's a dice, we have 6 values then, and then we're adding up 6 values together. It's not going to be, so, but to deal with that, we probably just divide by how many unique values there are. So here would be divided by 2, there would be divided by 6, and so on. But let's try this out and then we'll edit it slightly. So here you'd basically say, okay, you'd say it would be 0.2 minus 1, and then all of that squared. And then you do 0.8 minus 0 squared, so 0.8 squared. Probably should just open, let me open, I'll just not open a collab notebook for now. So this would be, this would be 0.8 squared times 0.8 squared. So point, yeah, that makes sense. So both. would be 0.64 plus 0.64. And then this would equal 1.28. 1.28. Okay, so that would be our difference metric. Again, it's not going to be out of any, it could be as high as it goes. It's not going to be bounded from 0 to 1, which is also slightly annoying. It is differentiable, so that makes it a little easier to work with, but I don't think this is an ideal working situation. Let's see if I could. I wonder if I could see. Oh, I guess I could. Okay, maybe if I could see. Oh, it's a little behind. Okay. Oh, I guess I could. How you doing? Okay, so this way at least I have a view of chat if anyone wants to say anything. Okay, maybe if I could see. Yeah, it's a little behind. Okay. Oh, let me know if what I'm doing seems interesting at all. How you doing? Okay, so yeah, so this would give us 1.28, and this would give us some sort of view of chat. Not supposed to be better than KL divergence in any means. I'm just trying to see how I would work. It's a little behind. Okay. Oh, let me know if what I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28. So this would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. Again, I mean, probably how I would work. It's a little divide these by how many instances there are. So it would be. Let me know if what I'm doing seems interesting at all. Divided by 2. How you doing? Okay, so we get to 1.28. So this would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. Again, I mean, probably how I would work. It's a little divide these by how many instances there are. So it would be. Let me know if what I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28, would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. I mean, probably divide these by how many instances there are. So it would be. Let me know if what I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28, would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. I mean, probably divide these by how many instances there are. So it would be. I mean, I know it's wrong. What I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28, would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. I mean, probably divide these by how many instances there are. So it would be. I mean, I know it's wrong. What I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28, would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. I mean, probably divide these by how many instances there are. So it would be. I mean, I know it's wrong. What I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28, would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. I mean, probably divide these by how many instances there are. So it would be. I mean, I know it's wrong. What I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28, would give us 1.28, and this would give us some sort of view of chat. Would not supposed to be better than KL divergence. I mean, probably divide these by how many instances. I mean, I know it's wrong. What I'm doing seems interesting at all. How you doing? Okay, so we get to 1.28, would give us 1.28, and this basically use view of chat. Would not supposed to be better than KL divergence. I mean, probably divide these by 2.
I feel like it's
I mean, I know it's wrong,
what I'm doing seems interesting at all. How you doing?
So we get to 1.2, give us 1.28. Like, so basically, I guess taking
You
it
down
down
bad,
to
you like
like
that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel like it's
I mean, I know it's wrong,
what I'm doing seems interesting at all.
seems like
How you doing?
so we get to 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel like it's
I mean, I know it's wrong,
what I'm doing seems interesting at all.
seems like
How you doing?
so we get to 1.28, give us 1.28. Like, so basically, I guess taking it
You down bad, you like that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel like
I mean, I know it's wrong. Right now, I'm just
seems
going to
interesting at all. How you doing?
so we just get our 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to
seems interesting at all. How you doing?
so we just get our 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to
seems interesting at all. How you doing?
so we just get our 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to
interesting at all. How you doing?
so we just get our 1.28, give us 1.28. Like, so basically, I guess taking it
You down bad, you like that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to
interesting at all. How you doing?
so we just get our 1.28, give us 1.28. Like, so basically, I guess taking it
You down bad, you like that.
it's not supposed to be better than
Yeah, divergence is probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to
interesting at all. How you doing?
so we just get our 1.28, give us 1.28. Like, so basically, I guess taking it
You down bad, you like that.
log
Divergence
vision
is
of
probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to log.
how you doing?
So we just get our 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
log
Divergence
vision
is
of
probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to log.
how you doing?
So we just get our 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
log
Divergence
vision of
is probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to log.
how you doing?
So we just get our 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
log
Divergence
vision of
is probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to log.
how you doing?
So we just get our 1.28, give us 1.28. Like, so basically, I guess taking
You
it
down bad, you like that.
log
Divergence
vision
is
of
probably
divide these by 2.
I feel
I mean, I know it's wrong. Right now, I'm just going to log.
how you doing?
Sorry about that. I need to find a way to. Is there no way to? Okay. How to view? What you guys are gonna quickly learn is I'm terrible at spelling. Widget application. Social Stream Ninja. Window capture method. Okay. For now, I won't be able to see comments. I'll see them later. Sorry, guys. Okay, let's see. So this is KL divergence. and this was, I guess, our own custom method, which we ended up at, mean squared error, which I think would work because you're just trying to. I mean, it's another loss function, so it tells the difference between distributions. I guess the question is now, why do we use KL divergence when we could use mean squared error? I have a few ideas in mind. Like, I know logs are pretty efficient when it comes to dealing with long strings of numbers, and we're going to be dealing with probabilities, and yeah, it's probably going to be most of it. So let me explain what I'm thinking. So let's say we had this case. Grab this again. So let's say we had this, but we had it with a lot more numbers. And let's say the prediction probabilities were a lot smaller. We had a bunch more prediction values, and they were a lot smaller of 0.01, let's say 0.21, 0.31. Let me just look. 0.01 again, and then dot, dot, dot. Let's go dot, dot, dot. We have a bunch of predictions, and then, our true values are probably going to be 0, 0, 1, 0. Oh, say I have one value. And then dot, 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 and so on. We understand the point, I guess. We just have a lot bigger question. And then if we used mean squared error here, we're going to end up getting, I guess, we're going to end up squaring, 0.01, let's say 0.02 minus 0, 0.21 minus 0, and we're going to square this value. Squared, I mean, I don't know why I'm going through all this, because I could just say 0.02 squared. 0.021 squared. 0.0041. So that's 0.0041, I'm pretty sure. And we're going to do this a lot. But we're going to add these numbers up. But the main point is that we're going to be dealing with very, very, very small numbers, and you're going to take the squared of probabilities, and this could even be, even smaller than 0.021. And let's say we have like a million classes, like in some ChatGPT models or some LLM models. So yeah, this could be easily an issue with mean squared error, and that's probably why they went with KL divergence. KL divergence deals with this, I guess, with the log function. Because I guess like a simpler version of what they're doing here, it seems like it seems like a weighted average between the differences. Like if we took away the logs, like if we imagine this without any log functions, it would be, I guess, a little easier to understand. It's basically, this feels like very weighted average because we're taking, 0.2, 0.5, and 0.3. Lower 0.3, and we're multiplying times the difference between the two values. Okay, and I guess we use the log function. This way it deals with smaller values a lot easier. Like, let's just do this one, but with log functions. So it'd be log, go here. So in our case, it would be 0.021 and 0. So it would be the log of 0.021 divided by, I screwed myself a little. Let's say this is just a really small value, 0.001. sort of equals that now. Okay, divided by point point oh oh one. I don't random point. I don't understand why some people use the zero in front of the decimal and some people don't. I personally don't do it so much just because I feel like it's a waste of time. But I guess it looks a little nicer, but I don't know. Yeah, I don't know. I like writing it like this. It feels like I understand it's, milliseconds, but I don't know. I just enjoy the .001 versus 0.001. Let me just, and then we do this times the probability of p, which we'll assume is the first value here, so it's 0.21 times this. Okay, 0.21 times this. Let me just grab this. So that's 1 point, yeah, so this is times 0.21. So it would give us 0.27 at the end. 2.7. And yeah, so using logs just helps us deal with, I guess, the issues of, of just dealing with smaller values. And since these, in most cases, these are going to be probability distributions of a model, and sometimes there'll be million, let's say this, I mean, there could be millions, but there could be a lot of, like, hundreds of thousands, especially new LLM models. They have, I guess you're predicting all the possible tokens. I'm not sure how much tokens are currently used in LLMs, but yeah, every probability could be extremely small, smaller than these values, and using, I guess, a mean squared error approach for, it works. I guess it would work when it comes to just, oh, how different is, in the beginning we started with two different coins, coin one and coin two. And in this case, mean squared error would work. I mean, it would tell you the difference between these two coins, and it would give you some metric of how to determine how different these distributions are for coin A versus coin B. And then, we tried it with a little larger example, and it works. Mean squared error is mean squared error, but in a big, in the larger examples of bigger probability distributions, mean squared error probably will break down because you're just going to deal with very, 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 very small numbers versus, KL divergence deals with those small numbers a lot easier. It seems like KL divergence is just the weighted average, like in regards to P. You could do it in regards to Q if you want, but it's the weighted average between the differences, uh, the log differences. Yeah, so I'd assume, and I know there's other methods to do this, but I mean, KL divergence is widely used. Okay. Um, right now we could also go into talking about, because I'm still a little interested in the log function right now. Let's say, let me explain what I'm thinking out loud a little more. Let's move this down. If I just did 0.2, I guess we would run it the same issue. I was thinking 0.2 and times 0.2 minus 0.6 plus 0.5. Let me just remove the log functions. Times 0.3 minus 0.2. I mean, again, I think we would get a value, but as these numbers, I guess this would work slightly better than mean squared error. It would work slightly better than mean squared error because now we're not squaring it. But then we're going to sometimes get negative values. I mean, logs could also theoretically be negative, if I'm remembering correctly, if the log function is. Just make sure that's true. Images. Oh. Yeah, so regular log, that's log x plus 1. Yeah, regular log is that. So yes, we can have negative numbers. So I guess this would theoretically work. We would, again, we're going to deal, like, let's say this number is very small and we're multiplying times another very small number. So KL divergence will be better than this, but I see, I guess I understand why KL divergence is the way it is. It seems like it's a weighted average between the differences in terms of P. Okay. Okay, I'd say I understand KL divergence relatively well at this point. Uh, if you guys want, you could, go to DeepML and implement it. Uh, there's nice examples, good learn section here. I need to fix this up. This is ugly. Nobody wants to see this. I need to go through all the questions and just fix all these small issues and make sure everything looks nicer. It's on the to-do list. Other than that, yeah, I gotta, I gotta go right now. But this was fun. I should do more of these. Let me know if you guys like them. I'll see you. I'll talk to you later.